Hi, greetings. I'm Sir Bren and I'm here to discuss the simplex minimization problem. Okay, we have here an example. We have a min z is equals to 10x1 plus 3x2, subject to two constraints, x sub 1 plus 3x2 greater than or equal to 5 and 3x1 plus 2x2 greater than or equal to 8. So we have a inequality sign which is greater than or equal, which is common to minimization problems. Okay, so we solve this and we will discuss the steps along the way. First, we transform the new um, objective function by adding artificial non-negative variables and slack variables. So this is the objective function. We have now min z plus the artificial non-negative variable coupled with the big M, and then we have zero coefficient slack variables. Take note that if there's two constraints, we have also two slacks and two artificial variables. Okay, and then remember that in minimization problem simplex method, that max is negative min z. Okay, for the constraints we have x sub 1 plus 3x 3x2, and then we include also slacks or slack. So we have for the first constraint we have slack 1, and then we also include a artificial non-negative variable a. For this one is a sub 1, and then we change the inequality to equal sign is equals to 5. For the second variable we do that also. We include s sub 2 or s2, and then a2 is equal to 8. Next step, we will solve this. So our objective function we equate to 0 becomes this one, and then take note that m we will assign a numerical value. So m is a big number, so if it is in 2 digits we assign 3 digits. automatically these slacks are 0 because it has 0 coefficients. And then I said that we equate this to 0. Okay, and then we include this, and then in including this we multiply these two constraints by negative 100. So uh, our purpose is to cancel the a1 and a2. That's why we multiply it with negative 100. Okay, for the first constraint it becomes take note that this is a sub 1. Take note that this will be cancelled later. And then our right hand side values becomes negative 500. And for the second constraint, or this one, becomes and then 100 a2. This will be cancelled. Is equals to negative 800. And then now we will perform mathematical operations. This becomes negative 390 x1. This becomes negative 497 x sub 2. Then these two will be cancelled, and then for s sub 1, 100 s sub 1 plus 100 s sub 2 is equals to, this is negative 1300. Now we've done with the objective function. We will build the first table. The first table for the row part, we will write the artificial variables a sub 1 and a sub 2, and then the objective function z, which is minimization. Remember that we do not include the slack. And then for the row, we have x sub 1, x sub 2, a sub 2, right hand side. And then later we will compute for the ratio. You can put lines, but for the purpose of this tutorial, to shorten it somewhat, and we will not provide lines. Okay, so now for the first table, you will refer to the previous equations. So for a sub 1, we refer to this, okay, to this equation. For the x sub 1 part, this is the coefficient is 1. For x sub 2, we have positive 3. S sub 1 is negative 1. We have no S sub 2, so we put 0. For a sub 1, we have 1. Coefficient is 1. We have no a sub 2. And the right hand side is 5. RHS stands for right hand side. Okay. For a sub 2 row, similarly, we will refer to this. We have 3, 2. S sub 1 is 0. S sub 2 is negative 1. A sub 1 is 0. A sub 2 is 1. Right hand side is 8. And for the z, we will refer to this one. We have 390. We have 497, negative 497. We have S sub 1 as 100, S sub 2 as 100. And then both A sub 1 and A sub 2 are 0. And the right hand side for z is negative 1, 3. Okay. So next step is to get the entering variable. So the entering variable, we will refer to the z row, and we will get the lowest z value, which is negative 497. We will encircle this and mark this as the entering. So entering variable, this enters. And then for the leaving variable, we will solve for the ratio. So the ratio formula is RHS divided by the intersectional element. So the intersectional element lies here at the entering column. Okay, so we have 5 divided by 3. That is 1.67. In here, we have 8 divided by 2 is equals to 4. And then we will not include the z. So only these two. And then next step is to get the least or the lowest among the two. And the lowest non-negative value is 1.67. Therefore, this is the leaving variable. Okay, this is the leaving. So we put leaving. This will leave. Again, x sub 2 or x2 will enter and a sub 1 will leave. Now we will develop the second table. By the way, this is the initial feasible solution, which is 1,300. Okay, now we will develop the second table. As we said that x sub 2 will be the entering. It will replace a sub 1, and then we just write a sub 2 and z, and then we copy the existing column variables as above. Okay, and then we will first develop the x sub 2. Okay, x sub 2 has its formula. Okay, we just adjust this. For x sub 2, the formula is all data for the new row. We have all data divided by the pivot element. Okay, so what is the pivot element? We know the old data, 1 3 negative 1 0 1 0 5. Okay, that is the old data, and the pivot element is this one, the 3. Okay, so for x sub 1, we have all data 1. All data is 1 divided by the pivot element 3, so 1/3, and then x sub 2, we have all data 3 here divided by 3 is 1. Okay, we do that to the other variables. We have here negative 1/3. This is negative 1/3. We have 0 divided by 3, or 0. We have 1 divided by 3, 1/3. Then for a sub 2, 0 divided by 3, we have 0. And then for the right hand side, we have 5 divided by 3, or 5/3. Okay, that is the first step for the second table. So the next step is to develop the other row values. Okay, so the a sub 2, for a sub 2 and z, we have this formula. The formula for a sub 2 and z is elements of old row minus quantity intersectional elements of old row multiplied by the corresponding elements in replacing row that will be the element in the new row. Okay, let's do that for a sub 2 and z. For a sub 2, we refer to the elements of the old row, a sub 2. Those are 3, 2, 0, negative 1, 0, 1, 8. So we write those here. And then the minus sign. Next, intersectional element of the old row. So that is for a sub 2, that is 2 here. So we write 2 to all of these numbers, and then we put the parenthesis or bracket, then multiplied, we said we multiplied it with the corresponding elements in the replacing row, which is here we solved earlier. So we write it here, 1/3, 1, negative 1/3, 0, 1/3, 0, and 5/3. And then we perform mathematical operations. Here we have 7/3. This is 0, 2 minus 2. This is 2/3. This is negative 1. This is negative 2/3. This is 1. This is 14/3. Okay, that is for the new a sub 2. Now we will do this procedure also to the new z. Okay, for the new z, we will do the similar formula. We will get the elements of the old row, which are negative 390 and so on. Okay, so we list here. We have negative 497, 100, 100, 0, 0, negative 1300. Then minus parentheses, or you can use brackets, the intersectional element of the old row. So this is the intersectional element, negative 497, we write negative 497 to all, of the formulas. Then multiplied by the corresponding elements in the replacing row, which is same as this one. That is 1/3, 1, negative, 1/3, 0, 1/3, 0, and 5/3. We perform now the operations. Here we have negative 673 over 3. Here 0. Here negative 197 divided by 3. Here 100. In here we have 497 divided by 3, which is positive. Here 0. And last one, negative 1415 over 3. Okay, now we will fill up the second table with these values. So we will write these and these to the new table, or our second table. So this is the second table. This is the values. Take note. We have 7/3. You have 0, 2/3, negative 1, negative 2/3, 1, and 14 over 3. So don't forget to double check. And then for z, the values here, we have negative 673. Oh, sorry. Over 3. Negative 197 over 3. 100. 497 over 3. 0. Negative 1415 over 3. Okay, now again we will check if it is optimized by referring to the z row. If it has negative values, still it is not optimal. We have not yet arrived with the optimal value. Okay, so now we will going to develop another table. We will develop the third table, since this has negative values. Okay, if it has no negative values except for the right hand side, it means that is the last table and we have arrived with the optimal solution. Since we have still negative values here in the 0 except for the right hand side, we still need to develop the third tableau. Again, in developing, we will do the same procedure with the first. As of the first table, we will also compute the ratio, and then we will get the entering and the leaving variables. Okay, for the entering variable, we will get the least or the lowest value in the 0, so that is x sub 1. This is the entering. And the leaving is we will compute the ratio. So we have RHS divided by the pivot element. We have 5 divided 5/3 divided by 1/3, that is 5. For a sub 2, we have this one, 14/3 divided by 7/3, this one, and that is 2. Then we exclude z. And again, this is the lowest, therefore this is the leaving variable. Okay, don't forget to encircle. Now this will be the leaving variable. And then again, we have here the third row. Same procedure. So we have the we just copy x sub 2, it remains, and the entering variable is x sub 1. No, x sub 1 is the entering variable, this one. And then we just copy z. And then for the column, we just copy the same variables. Again, the row we develop first is the entering row. The entering row formula is all data divided by the pivot element. And I will just write the answers. Same procedure as the second row. Alright. And then next is to develop the new x sub 2 or x2 and the z by using the formula, this one. This formula. So I will just write the answers. This is 0, 1, and RHS is equals to 1. For z, we will also do the same formula as we did with x sub 2, and the answers are okay. Now we notice that it still has a negative value in the 0, so it is not still optimal. So we will again look for the entering variable, which is this one, the lowest. Entering. And the leaving, we will compute for again the ratio. Though the ratio formula is RHS divided by this one, this intersectional elements. So 1 divided by negative 3/7 is negative 7/3, and 2 divided by 2/7 is 7. Now, which 2 shall we pick? We will pick the non-negative lowest. So we will not choose this, but instead we will choose this as our leaving variable. Okay, so now we are in the fourth row. We hope that this will be the last one. So x sub 2 remains, and x sub 1 will be replaced by s sub 1, and z always remains. And we just copy x sub 1, x sub 2, and so on. Okay. We will first develop the s sub 1 by using the formula, the steps in the previous tables. This becomes 7/2, 0, 1, negative 3 halves, negative 1, 3 halves, and 7. And then we will develop the new x2 and the z rows. This becomes 3 halves is 1, 0, negative 1 half, 0, 1 half, 4. And for the last one, the z, we have 231/42. We have 0, 0, 63/42, 100, 4137/42, and negative 252/21. Okay, now again we will seek the 0 if it is optimal. So like what I've said, if these are all positive except for the right hand side, this is optimal. Since all are positive, we can say that we have reached the last row. Okay, so our answer, our z min here is negative 252 divided by 21. That is negative 12. Remember that our max negative min z, like what I've said in the first discussion above. So if it is in negative, we will convert this negative 12 into positive. Okay, so that is our optimal value. Therefore, our answers are, we refer to the right hand side, For x sub 1, we have no x sub 1, so this is 0. For x sub 2, x sub 2 is 4, this one. For s sub 1, we have s sub 1, and that is 7. For s sub 2, we have no s sub 2, that is 0. And of course, we have no a sub 1 and a sub 2 left. And then our mean z from negative becomes positive. Okay? So that's it. Thank you very much. Don't forget to subscribe. Happy learning, and I will see you on the next video. Thank you.